Hello, my name is Bridget Mizuko, coming to you from Gulf Coast Ultrasound Institute with today's hot tip to discuss how to calculate the aortic valve area using the continuity equation. First, let's go over what the continuity equation actually is. The continuity equation for the aortic valve area equals the cross-sectional area of the left ventricular outflow tract times the velocity time integral, or the VTI, of the left ventricular outflow tract over the VTI of the aortic valve. This is the actual continuity equation. We use the continuity equation to calculate the aortic valve area. A lot of people get confused because there are a lot of different ways this formula can be shown, all meaning pretty much the same thing. In this formula, also showing you how to do the continuity equation to figure out an aortic valve area, the formula seems a little bit different. Sometimes we'll see the continuity equation shown like this. This formula is just representing a simplified version of the previous full formula. When we break down how to calculate the cross-sectional area, we need to multiply 0.785 times the diameter squared to obtain that number. So this version is just showing you specifically how to calculate the cross-sectional area of the left ventricular outflow tract. This is another simplified version of the continuity equation in which the formula changes slightly to substitute velocities for VTIs. I always recommend using a VTI instead of the peak velocity because the peak velocity will be less accurate if the shape of the velocity curve is atypical. The reason why we always want to trace the Doppler waveform when evaluating the aortic valve and not just use the caliper to measure peak velocity is because tracing the envelope will also give you a mean pressure gradient, which is a measurement that is essential to severe aortic stenosis. It will also give you all of your other values, such as a stroke volume of the LVOT, mean and max velocities, and a maximum pressure gradient. So what exactly does this all mean, and how do I obtain these measurements in my study? Let's go over to the machine and take a look. The first thing we need to do to calculate an aortic valve area is to obtain a parasternal long axis view and cine loop to get to early to mid systole when the aortic valve is at its maximum opening. We then need to do a diameter of the LVOT measurement. We do this measurement right before the opening of the cusps, and we need to make sure that we enter it into our system so later on when we go to do our velocities in apical 5 chamber, the number's there. The next thing we want to do is get a velocity, or a VTI, of the left ventricular outflow tract. So we put on our color, and we put on our pulsed wave Doppler. And we want to make sure we trace the waveform, starting from the baseline. And this is to make sure that we're getting our VTI. And as you'll notice, when I traced it, I'm getting a VTI, a max velocity, a mean velocity, a max and mean pressure gradient, and I'm also getting the stroke volume of the LVOT, which some doctors are going to find really important. The last thing we're going to do to get the aortic valve area is do continuous wave Doppler right through the aortic valve. We're going to freeze the image and cine loop through it. And then once again, we want to trace the envelope so we can get our VTIs. When I'm done tracing this envelope, the aortic valve area is going to pop up because I did all of my 3 steps. So once again, I have an aortic valve area VTI, and then I actually have an aortic valve area that was used calculating using the maximum velocities. And that's how you calculate an aortic valve area using the continuity equation. 3 simple, easy steps. Now you give it a try.